All right. We'll quickly recap what we were doing in the last class. And we were looking at the Laplace transform, and then we talked about the Dirac delta function earlier on. And then we said that we started by saying that the Laplace transform of the delta function is obtained by looking at the definition of the Laplace transform. Actually, all functions, the Laplace transform of all functions you are going to get by starting by looking at the definition of the transform. So we put the definition of the delta function, delta t minus tau, and you plugged in the values, and what you came up with was the Laplace transform of delta t minus tau is e to the minus s tau. And you can therefore also say that Laplace transform of the delta is going to be equal to unity because tau is going to be equal to 0. And another thing that we also mentioned is that k times the delta function, when you integrate, you're going to get k. With that background, what we said was that we'll start looking at the differential equation, and we are looking at first order differential equation only as a vehicle to understand the more general forms. But it is illustrative to look at some kind of a example type of thing rather than completely abstract, which we will do in just a little while. So we started with the same good old example that we had, which is y prime minus ay is delta t and y0 equal to 0. Take the Laplace transform on both sides, do the algebra, and what we got was the Laplace transform of the function y is equal to 1 by s minus a. Okay, that's if you have the delta function. And you can go ahead and use any resource. Last time we used something called Symbolab. That's not the only online resource that's available. There are a number of them available. For this particular example, I had used that. For future examples, I'll use one or more of the others. So all of them are extremely good. You are welcome to use any one of those online resources. Okay. Once again, today I'll work out an example where the partial fractions and all that will be there, but that's only just to illustrate and not to ask you to do that. You can go ahead and use the online resources. Okay, so you can use the online resource and see that your y is going to be equal to e to the at, and if you have a forcing function which is k times delta t, then y will become equal to k times e to the at. And if you have now the equation as delta of t minus tau on the right hand side, then you can proceed in the similar fashion to get whatever you are seeing downstairs. But physically, the y0 equal to 0 is quite important, as we will see as we move ahead. Okay, and the solution that is obtained is e to the at minus tau, and I say it's not surprising because the initial condition is homogeneous. So what we mean is that because, so I've got something like that, and my expression was there, and then y0 equal to 0. And if I have got t minus tau hanging in there, then remember that this guy means that everywhere there is no signal except at t equal to tau. Okay. So therefore, subsequent to t equal to tau, something is going to happen. For this particular case, we have an exponential that is likely to go like that, and when t is equal to 0, the exponential is likely to go like that. Okay. And if I'm interested in the solution at some time t which is greater than tau, then I just have to take e to the a t and then replace t by t minus tau, because nothing is happening up to this point. Downstream of this point something is happening, and the t is nothing but t minus tau. So this guy here is t minus tau. So that's why I say it's not surprising that you get the solution as e to the a t minus tau. And in general, we said that if this guy comes up with some kind of a y star, right? So this need not be this. Suppose I just say that this is some function, I don't know what that function is as of now, y prime, y, and the solution is going to be equal to y star for delta t. The solution is going to be y star t minus tau. That's what we mean when we say that the solution is going to be coming to just simply replacing t by t minus tau, for the simple reason that y0 is equal to 0. So that's important in this. Okay. All right. Then what we said was that I'm never interested in the delta function. I'm always interested in a right-hand side that is going to be there. And the right-hand side, therefore, we just said was equal to some function f of t. Okay. So this guy f of t now has to be represented in terms of this delta function. We have spent so much time talking about the delta function, so there must be some use to that. So if I have got a function f of t, this is f of t, could be some crazy function. I'm not bothered about what the dependence is, but what we say is that a function, right? A function is nothing but a bunch of values at a bunch of, let us say, t's, right? So therefore, this guy, this function is made up of this, at every location on the x-axis. I've got some value on the y-axis, and that's nothing but this function f of t. Okay. And luckily, everywhere the delta function is 0 except at a particular location, and therefore what we say is that my function f is going to be the summation of f of tau, which is some arbitrary dummy variable as of now, and then I have this delta tau, that's the impulse function, that's the hat that is on top of it, and delta tau is equal to unity, and therefore as and when my delta tau is going to get squeezed to 0, delta hat will approach delta and I will get the full function back. So that's basically the representation of this particular function using the delta function or the impulse function, if you will. Okay. All right. So what we therefore said was that I've got now f of this guy here was equal to a functional representation, and this representation is going to be now equal to summation of f of tau n, where tau n is some kind of a dummy variable, delta hat t minus tau, and then delta tau. Okay. So as and when my delta tau is going to be squeezing down to 0, this becomes exact. Okay. But what we have also learned in the past, which is very, very nice about these linear functions, is that if I've got a right hand side, now I'm going to just open this guy up and say that this is tau 1 delta t minus tau 1 delta tau plus f of tau 2 dot 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 dot. So that's what has been written up there. Okay. So this function which was there is now represented as a sum of infinitely large functions on the right hand side. Okay. Now, using the linearity property, then what we said was, this once again we'll go back to the example to be used as a vehicle, y1 plus y2 plus dot 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 dash plus a times y1 plus y2 plus dot 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 is equal to that. Okay. Remember, this is a linear function, and therefore we are saying that a linear sum of the solutions is also a solution, and therefore I'm plugging that back into the equation. Okay. Once I do that, then I say that I'm going to just remember we said that we did the same thing when we tried to say that the solution to the differential equation is going to be the sum of the complementary function plus the particular integral. Exactly the same procedure, and we are going to say this n number of times so that I drill it into you, and that's the key to all of the solutions of linear equations. Okay, so what we now say is I'm going to split this guy into n number of equations. Okay, so I'm going to say that this guy, and I'm perfectly legal in doing such things. Now we are going to say that y1 plus or y1 prime plus ay is equal to the first term here, which is this guy here, right? So this guy is equal to this guy. Similarly, I say y2 plus ay2 is going to be equal to the next guy, and then so on and so forth. Okay. So what we have said is that y minus ay is equal to this. This is the summation, and now we are saying that we have split this into n, where n is a very, very large number, and now we have got n equations, okay, where n is a very large number. Now, that's where the linearity ends. Okay, so it's not enough to say that my equation is linear. I need to also worry about the initial or the boundary condition which is there, which is why we want that 0 in there. All the time we'll be obsessed with this 0 out there. Okay, so what we said was that my initial condition y0 was equal to 0, and y1 plus y2, because we are hypothesizing that y is y1 plus y2 for n terms, this is also equal to 0. And if this be the case, then I can easily say that each of these guys can be hypothesized to be equal to 0. Okay. Once again, you can make life difficult for yourself by saying that y1 is equal to minus of sine theta, y2 equal to plus sine theta, and then say that I'm going to use that. That's perfectly fine. But then I don't want my life to be more difficult than what it already is. So I just say that y1 equal to 0, y2 equal to 0, y3 equal to 0. So that's the beauty of having 0 on the right hand side. Okay. So we have now successfully split that original differential equation that I had into n differential equations where they are all complete in the sense that I have the equation, I have the initial condition, and all of these guys have 0 as the initial condition. And now we already know that the solution for each of these guys, is known already, because we have already obtained the solution for y prime plus ay is equal to delta y0 equal to 0. each of these guys looks like that, right? So all that I need to do is sum up each of these guys. Okay? You take the sum of these guys and you have the solution that you are looking for. Okay? So the sum of these solutions is going to be equal to just simply the summation of that. And then I'll just, because my n is tending to infinity, the summation is going to go to an integral, and you get y is going to be equal to integral of f of tau. F of tau, remember, is nothing but my right hand side. Okay, so whatever was there, some function g y prime y is equal to, this was my original equation. So all that I have is this times y star t minus tau d tau 0 to t. That's my y. Okay, the solution to the differential equation is in this particular form. All right, so this is where we stopped last time, and now let us just go ahead and continue. Anybody have any trouble with that? All right, so let us go ahead and continue now with something else, or we'll just take it forward a little bit by looking at an example. Okay, before we go ahead and, so there has been a fair amount of algebra that has gone into trying to get this solution, okay? And there's a reason for that algebra which will become apparent as we move along, but you can also get the same thing by looking at my Laplace transforms, and we'll quickly do that before we move ahead. So now let us say that the same situation exists, and now we go to a slightly general plane, and I just say that there is a function g which is a function of y prime and y, is just like y prime plus ay equal to something, and this is equal to f of t, and y0 is equal to 0. All right, so if this be the case, now let me say that we would like to use the Laplace transforms. Okay. In the previous so-called analysis, we just said that we took the equation, we had the Dirac delta function on the right hand side, and then we integrated it in some sense and we obtained the solution. Okay. So let's just go ahead and take a slightly different approach and see what we get. Again, we'll wave our hands a little bit as we move along. Okay. So I'll take the Laplace transform on both sides. I've got the Laplace transform of this entire function is equal to the Laplace transform of whatever is there on the right hand side. Okay, so what will be this here? What will be the Laplace transform of this particular left hand side? Remember, y0 is equal to 0. Do I need this for the getting the Laplace transform on the left hand side? Remember, this guy is some y prime and some y, right? So what is the Laplace transform of this? What is the Laplace transform of this? This is equal to what?
L of y plus S of y0.
Okay, so L of y times S minus y of 0 plus A times L of y, correct? Okay, so on a general plane, we will just say that this guy is going to be, the Laplace transform of this is some function g of s times, would that be okay? Just some kind of a generalization and nothing else. I mean, I'm not doing anything very profound, just plugging in the number, and I'm saying that there is going to be a function of s, which I'm calling it g of s. That s minus a which was there, I'm calling it g of s. Okay, all right. So times L of y is equal to the Laplace transform of this guy, which is L of f, and let me just say that this guy is some function of s, so we are calling it an f of s. Okay, so we'll call this a g h of s to be consistent with what is there. Okay, so whatever is there here, I'm taking the Laplace transform, I'm calling it h of s, and then there's going to be a Laplace transform of y, which is going to be equal to f of s. No big deal. So I get Laplace transform for y is going to be equal to f of s upon h of s. And therefore, what is y equal to? What is y equal to then? Laplace inverse of whatever is there inside, right? So this guy is Laplace inverse of f of s upon h of s. Okay. Now, what is Laplace inverse of this here? Okay. One is tempted to write Laplace inverse of h times the Laplace inverse of 1 by h, but that's not the case. And we'll bring in now a definition before we go ahead and do anything. Okay. So this guy here is written up as, okay, this we are not proving. We are not proving this. Okay, it's a straightforward proof, but we don't want to do that here. So y is going to be the Laplace inverse of, if the Laplace inverse of some function divided by some function, then you can write y as equal to Laplace inverse of fs convolved with the Laplace inverse of 1 by hs. Okay. This is a definition. Okay. So this is a definition as far as we are concerned. So this is the convolution operator. Just a definition, nothing else. Okay, we are not proving anything, we are not showing anything. We are just saying that this guy who is there, Laplace inverse of f of s by h of s is going to be Laplace inverse fs convolved with Laplace inverse of 1 by hs. And what is Laplace inverse of fs? What is inverse of Laplace hs? ft, right? Because remember we had, this is ft, we took the Laplace on both sides and we said that this was cap fs, and so the Laplace inverse of this is nothing but f of t. So y is going to be equal to the f of t times, in quotes, f of t convolved with Laplace inverse of 1 by hs. Okay. Okay, what is this convolution now? Okay. We'll just look at the definition and that's about it. Okay. So the convolution of two functions. So you have got the convolution of two functions, some function k convolved with some function j is equal to integral of k of tau j of t minus tau d tau, which is also the same as integral of k of t minus tau j of tau d tau. Both of these are equivalent. So I've got two functions. Both of these are, let us say, functions of the variable t, and what I'm saying is that k convolved with j is going to be integral of this 0 to t, integral of k tau j t minus tau kt minus tau j tau d tau. It's just a definition and nothing more than that as far as we are concerned. Okay. So we define a convolution operator which is looking something like this. Okay. So have we seen this type of thing before? Have we seen this, not the operator, but this integral here? Have we seen this integral before? Something that looks like this? Yeah, because the previous solution was exactly that, right? Nothing but that, right? The previous solution we said was, for this guy here, right, we did some amount of algebra, and then we said that the solution to this was equal to f of t times y star t minus tau d tau, okay, 0 to t. This was the solution then, okay, and what you're seeing now is something very similar. So we didn't call it a convolution operation at that time. Now you can if you wish. Okay. So k times j, okay, this is, sorry. So k times j is going to be 0 to t k tau j times t minus tau d tau. This is equal to this. And once again, we are not going to do it, but if you're really interested in showing these two guys are equal, then you can just take a change of variables, put p equal to t minus tau, do a little bit algebra, and you'll be able to show that both of them are the same. Our intention is not to do that as of now. Okay? Our intention is just to understand that when you have got two functions, if you have got something like this, then this is nothing but Laplace inverse of fs convolved with Laplace inverse of 1 by hs. Okay, so that's our intention, and we are only users. We are not going to go ahead and do any showing of any of this. Okay. Okay. All right. So there is this convolution operator, and we say that when you have got two functions f and y star, the convolution operation is going to be equal to this. Okay. Now, if now I go ahead and look at this again, right? The solution to this we said was g of some y prime and y is right hand side, and we said that y is going to be now equal to f of t times Laplace inverse of 1 by hs. This is my solution. Okay, and this is equal to integral of f of t, and the Laplace inverse of this, let me call it a g star. Suppose I call it a g star. Okay, and this will be t minus tau, d tau, 0 to t. Was it the same as what we had in the previous derivation? Is it the same or is it different? Okay. This guy here is what I have obtained by using the Laplace transform and we have waved our hands a little bit and said that there is something called a convolution operator, and if you are taking the Laplace inverse of that, we have not proved anything. We just said that you are going to get the Laplace inverse of the ratio of two functions as the convolution of these two, and when you did that, you came up with this here. Is this the same as what we had in the past for the solution? It has to be, right? If it is not, then whatever we are doing is total bunkum bogus, right? So it has to be the same, and it is, right? So either way, whether you take this route or you take the previous route, you are coming up with the same final expression. Okay, anybody have any trouble with that before now we go ahead and try to use this guy in an example? Both these approaches are important, and the first one more so because the first one is what we are going to be using later on, quite a bit later, maybe post midsem sometime, when we are looking at partial differential equations. That's why both these approaches have been put forward upfront right now. Okay. All right, if there are no questions, let's go and look at. There's one question, of course, somebody had asked about the value of the function at 0, which was not matching the initial condition. I said we will take care of that later on. We will take care of that later on. Okay. Apart from that, anything else? All right, so let's now go back to our favorite example, which is, we have already done this twice, once by simply splitting the equation, once by using the Heaviside function, and now we'll use the so-called Dirac delta function and get the solution. So any of these is perfectly fine when you are looking at a situation like this, but it just turns out that sometimes a particular approach is maybe slightly different or slightly easier than the other approach. So y prime plus ay minus is equal to f of t, and f of t was equal to this. Okay, so this is f of t. It was flat up to t equal to 0, and then t equal to 1, sorry, and then it became equal to 0. And now let us go ahead and use whatever we have obtained and see if we don't get the solution. Okay. So what have we done now? How would we approach this? What should we do? How do we get the solution to this now? Based on whatever we have been doing in the last, this class or the previous class. How do we go ahead and solve this?
First find the y star and then take the combination.
Okay, so first find the y star. And what is y star? What is y star? The response to delta. Okay, so my first approach would be to say that I would like to find what is the solution to this equation with my right hand side as being equal to the delta function. So my right hand side is delta function, and this is there, right? And I am going to get me the solution. Okay, so if I go ahead and use the Laplace transform, this is the last time we are going to use this example. So the Laplace transform of this guy is Laplace transform of y prime minus a times Ly, and this is L of delta. What is L of y prime? S, and then minus of y0 minus a times L of y is equal to 1. and using this condition here, this guy is 0. So the Laplace transform is 1 upon s minus a. And this anyway we have worked out in the past, and this is e to the at. So this is my y star. Okay. So y star is equal to e to the at. So my y, which is the solution to this, is going to be equal to, this is the right hand side, and then e to the power of a t minus tau d tau. Okay, that's about it. That's my solution. Okay. All right. Now let us just go ahead and do a little more algebra and find out whether this is the same as what we have. Okay. Y is 0 to t f tau e to the a t minus tau d tau. So let's go ahead and integrate this guy. Okay. Any trouble up to this point here? I'm just using that star symbol to indicate the convolution, but that's not really required if we are saying that we have come using the earlier approach. Okay. All right. So f tau, let's go ahead and integrate it, and there's a reason why I want to do the integration. So this is going from 0 to t. Suppose I'm interested in somebody here. Okay, my time is t, which is less than 1. What would the integral be? Y is equal to integral of, this is 0 to t, right? So what would be the limits on this integral? 0 to t. Okay. What is f tau? F tau is 1, right? This is f tau. This is 1 up to t, because my interest is only up to t. I'm not interested in downstream of this particular location, which is 1. So 0 to t, f tau, which is 1, e to the a t minus tau d tau. Okay. So if my interest is in t less than 1, then I go ahead and say that y is going to be equal to 1, which is 1, and then y star t minus tau, which is e to the t minus tau. Okay. All right. You can do the algebra now. Okay. So it's straightforward integration that's going to happen, and you go ahead and do blah 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 blah, and finally you are going to come up to the solution. Okay, that's not difficult to do. All right, now suppose t is greater than 1. Now this is when t is less than 1. What happens when t is greater than 1? What happens to f tau? What happens to f tau when t is greater than 1? 0? This is f tau, correct? It is starting from 1 up to here, then it goes down, and then it goes there. If it is 0, what is the solution if it is 0, for example? If y prime minus 8 equal to 0, y0 equal to 0. What is the solution for this? Y equal to 0. There is nothing happening. There is no forcing on the right hand side. The initial condition is 0. So y is 0. And if you say f tau is equal to 0, then nothing is there, right? But I know something is there, right? There will be a solution because up to t equal to 1, I had something. And then it became equal to 0. So f tau continues to be unity from 0 to 1, and then it is 0. Okay, so my interest is in time t here. Okay, the system has undergone a function on the right hand side which went like that and then it went like that. Okay, so this guy is going to have two terms, right? It's going to have two terms. Y is going to be integral 0 to 1 f tau. What is f tau 0 to 1? 1. F tau 0 to 1 is 1. E to the a t minus tau d tau. What will be the second integral? 0. Why should it be 0? Suppose this was the transient. It did not go to 0. Then it would be this number here. In this particular case, this is the transient, right? So I'll just say 0 times e to the power a t minus tau d tau. Okay. So if I am talking about this integral here and my ft is this, then from 0 to 1 I have this integral here and subsequently I have this integral here. This has taken care of this condition as well as this condition when the system is at this particular time. Okay. Algebra you can do. Okay. So you go ahead and do the algebra and you will find that this guy and this guy, the solutions to this are the same as what we had previously by using the Heaviside function approach. Okay. All right. Anybody still having trouble with this? We're going to leave this now. Okay, for one last time, let's do it again. If we have got a function, right, I've got a left-hand side, which is some differential equation. At the moment, we will not worry about what that is. And the right-hand side is 0 and y0 equal to 0, right? If this is the scenario, then we say that my solution y is going to be equal to the function which is there on the right hand side, which is f tau, times what? Times what? Times y star. Times y star t minus tau d tau. And what is this guy here? What is this y star? Y star is the solution to this equation when my right hand side is delta. Okay? And we have shown it in a couple of different ways, and you can go ahead and use either of these approaches when you have got a right hand side which looks like that. Okay. All right, we'll leave this business here now and look at some other stuff. We are not looking at every first order differential equation that exists. We are now going to look at one last case and then say that we will not look at first order equations anymore. All right, so something very straightforward now. Dy dx, suppose I've got any, okay, so maybe by today evening, now that we have done everything about first order equations, there will be an assignment that will be uploaded. That will be due perhaps a week from today or a week from tomorrow. Okay. All right, so dy dx is equal to m of let us say x and y upon n of x and y. Suppose this is another equation that I would like to get a solution to. So I'll write this as minus n of x and y dy plus m of x and y dx is equal to 0. So this is my equation. So dy dx is minus of m by n. M and n are functional representations which are going to be given to us. Okay, now suppose we say that the solution to this can be considered as some function phi equal to a constant. Suppose. Okay, and if this becomes a total differential, then this becomes equal to 0, right? And d phi is del phi del y dy and del phi del x dx. This comes from straightforward calculus, right? D phi is del phi del x dx, del phi del y dy, and you see a parallel between these two, and if you want to know whether this guy is happening like this or not, then you take the cross derivative del del x of n, if you find is del del y of m, then this will work out. So you are going to be able to get a total differential if such a situation exists. Now many times this is not going to happen, and we use what is called an integrating factor. Sometimes, of course, this is something which may or may not work out. So we start with, once again, we start with the same equation, which is dy dx is equal to minus of m by n. So this is the equation that we are starting out with, and we are saying that we would like to know somehow if there is a factor. Remember, we had an integrating factor when we were looking for the solution to a first order equation, right? When we had y prime plus ay plus something is equal to 0, then what we said was we would take e to the power of integral a dt, and that was my integrating factor, right? So that's what we had then, and then we converted it into a total differential. You will attempt to do such a thing here also. You can attempt to do that. Whether it will work out or not depends on what these functions m and n are. Okay. It turns out that, suppose now I have got a function f. Now you are again hypothesizing that a function f exists that can do that. Maybe, maybe not. So f times m dx, we'll drop the xy, we'll assume that that's understood. Fm dx, fn dy is equal to 0. Okay. And if this is exact, okay, if this f is able to make it into an exact differential, then we have said that this is d phi, this becomes del phi del x dx, del phi del y dy, and then you will take the cross derivative and equate it to 0. So I would take del phi, we are assuming phi is a well-behaved function. Okay. So you have got del del y of f times m, correct? Del del y of f times m is equal to del del x of f times n. Okay. All this is happening, we don't know whether we are going to be able to get something or not. We are just doing in the hope that you're going to get something. Okay. All right. So this guy is like this, and now we make some statements which say that when will this work and when will this will not work. When will this work? Okay. So let's just say that suppose, okay, this is a big suppose. If it is not, then you just don't worry about any of this stuff. Suppose f is a function of x only. So you say that hypothesize, if you will. So if f is a function of x only, then what happens to the first term here? This here, what is del y of fm? If f is a function of x only, m is x and y, then what happens to this function here? Can I pull this f outside? Yes, because f is a function of x only. So this is fx, del m, del y. So that's this term here. And what about here? Can I pull it out? No, because the derivative is with respect to x. So we will say that this is equal to m times df dx plus n times f times del n del x plus n times df dx. Up to here, again, already remember that we have made a big if here. We have said that if f is a function of x only, then this happens. Okay, still no juice because I have to get this f. Okay, remember what's my objective? My objective is to make that into a total derivative by multiplying it with some function f. Okay, and we multiplied it, we came up to here, and now I have this here. Now can I get something out of this here? Now I take this to the left hand side, minus, and I say this is equal to this. Can I get a solution to this? We have looked at first order equations now. Can I get a solution to this? And if I want a solution to this, when can I get a solution to it? Okay. Let me just divide through by n. Okay, it's a first order equation, right? Df dx is equal to something. You can use whatever means that you have to go ahead and get the solution. Can I get the solution for this equation? Yes or no? Can we get a solution to that equation? And if we can, what is the right hand side? Right hand side is df dx. And what is the hypothesis? Or what is the assumption? F is a function of x only, which means what is this side here? This is a function of x only. If this whole junk here is a function of x only, then I have some hope. Okay? Then I have some hope of finding out this using whatever is that integrating factor approach or whatever that we have seen so far. Okay? Because this then becomes a first order differential equation. Df dx is going to be some function of x. I can go ahead and integrate it and get a solution. Okay? So, I mean, this is a big if. If at all this is there, then I can get something called the integrating factor, which I can use to get a solution. Now, it's not necessary that f is a function of x only. Okay, we stop here for today, and I'll see you again on Thursday. Thank you very much.